Hello, everybody, and welcome. We are going to get started now. It is super good to see a bunch of familiar faces, see a lot of new faces here, and we're very excited to have everybody joining us today. So, as I said, we're very, very excited. I'm so excited to be here that I did go the Pulsar blue for the occasion. So, also, if anyone's interested, I did also go Pulsar blue with the nail polish. We do have that at the sponsor booth, so if you also want to, you do have to do it yourself, but definitely an option there. And so firstly, I want to give a huge thank you to all of our speakers. We obviously could not have done this without you, and we have a really awesome lineup here today. I am super, super stoked about this, so make sure and talk to these people and ask them some good questions. And we also want to give a thank you to our CFP committee. We would not have been able to do this without them either. This is a very, very hard task. It takes a lot of work sorting through. We had a ton of submissions this year, and it really is, excuse me, a lot of work to get a really balanced and varied schedule put together. And I also wanted to introduce our MCs. So these people will be helping you throughout the entire day. And we have one MC per one for the morning, one for the afternoon for each of our breakout rooms. So feel free to talk to these lovely people, and they'll help set up Q&A sessions and introduce our speakers as well. And I also wanted to give a special shout out to everyone that made this happen. And this includes everyone at the StreamNative team, everyone who's here today, and also a huge shout out to my co-organizer, June, as well as Emilio, who did the beautiful designs here and was also working tirelessly at the last minute, putting a lot of hours in. So huge special thank you to all of these people as well. And last but not least, a big thank you to our sponsors. So StreamNative is our host. Our platinum sponsor is Verica. PingCap and OneHouse are our gold sponsors, and we have some wonderful community sponsors here as well. Feel free to check out all of the sponsor exhibit booths right outside this room. Very, very convenient. And we'd also like to give a special welcome to our community. So please feel free to join our community Slack space, our GitHub page. I'll try to leave this slide up here just a little bit longer so people can get pictures of that. And also, if you have any questions, the StreamNative Academy is a really great place to get started with any of your Pulsar questions as well. Again, I'll try to leave that up there for a second if people want to get photos. This slide also will be rotating throughout our breaks as well, so feel free to find it there if you need. Also, this is one of the things I'm very excited to announce today, is we have a podcast that we're going to be launching this year. So this will be a video podcast. Yes, oh, I see some excited faces. I love this. Yes, I know it's early. We haven't had our coffee yet, and I'm still seeing enthusiasm. This is great. So if you are interested in being featured on the podcast, or if you just want information, want to send the info to your colleagues, we're not going to pressure you. This will take you to a form. So if you want to get a picture of the QR code, this will also be rotating on our, the slides that will be here during transitions and breaks as well. So we would love to feature your Pulsar use cases. And this podcast is inclusive of all streaming as well as stream adjacent, anyone, the entire ecosystem around stream processing. It is called Crossing the Streams. So again, if you're interested, me and my coworker Julian will be hosting it, so you know it's going to be very fun. And we'd also love to see any social media posts. Feel free to use either of these two hashtags, and we will we'll like it, we'll check you out, we might give you a follow. So definitely feel free to post that as much as you want today. We'd also love to see what you learned. So if you learned something new today, if you met a new colleague, we'd love to hear about it and see it posted as well. And for our schedule today, so next up we'll be hearing from our CTO, Matteo, and then the rest of our keynotes. And we'll have this room and the room next door for our breakout sessions for the rest of the day. And then we'll come back here for our closing sessions, our closing keynotes. And if you've not downloaded the mobile app, that has all the information that you're going to need, all of your schedules and everything on it. And so definitely feel free to download that. And most importantly, my opinion, don't forget to pick up your swag. I'm ridiculously excited about the beanies and the shirts. So that is just at the booth next to the registration booth if you kind of turn the corner there. And with that, I'm going to pass it off to Matteo, and he's going to give the official first keynote of Pulsar Summit.
Thank you, Kato, for a nice intro. Showing up. Okay. First of all, like, welcome everyone to Pulsar Summit. Again, I'm also very excited for this year. It's the second time we've been here, like last year. And I want to start as well from where we left off last year. And our path for illustrate a bit the journey for the omni-comprehensive data streaming platform. We kind of started one thing we always talked about was about operational domain versus the analytical domain. And how in operational domain you have things like message passing between components, application and services, and analytical domain is more aggregating sources of events that has happened already and then analyzing them. And this is like a very broad classification that we've been using for long, but it is, I think it's useful to define the scope and the intention of the use case of the applications. And Pulsar has been one of the only systems that can play well in these two domains, right? The one thing that we've seen during the past few years, though, has been like that there is kind of a bit, the lines are getting blurred and blurred, and the use cases are kind of like intersecting a bit more. And there are a few reasons for that. One is that more and more use cases are very driven by data, so getting data, analyzing data, and then using that data to feed back into the core logic of the applications. And so this is kind of like one main motivation for these two domains to start crossing. And another way to tie back to last year Keynotes and narrative was that we kind of lay down the path that there are a few fundamentals of the modern data-driven application, event-driven application. And at the core, you have topics, which are kind of like the traditional pub/sub model. And you can see topic data in multiple ways, as a stream, or as a queue, or even as a table. And you can play around with the same data in this different form. You might need to have different access patterns, like either shared access pattern or exclusive access pattern, and with different processing semantics, at most once, at least once, and exactly once. And the final one was a different level of abstraction, meaning you might want to have different access level for different use cases. You might want to have high level with ease of use and very simple semantics, or more low level, but with more control and more freedom to do things in a more performant way when you need that. And if you look at it from a different perspective, so people look at these platforms in different ways. If you look at it from a developer point of view, developers are caring for some properties that are different from other perspectives. So if you ask the developer, typically, they want to use the best tool for a job. And for the best tool for a job, in this case, we typically think about what is the best level of abstraction. You need to provide a developer with the right set of primitives, the right set of semantics. And that has to be easy to understand, and it has to be easy to reason about. What are my guarantees if I do this? What happens if I use this API? Another thing that matters a lot to developers is feature richness. If you're trying to build a very complex distributed application, you have already a lot to build on your plate. And you want the platform to provide you to solve all the hard problems around distributed messaging and building things that are durable and scalable, and that can take away a huge part of the application developer job. Just saying that you have a low-level distributed platform, if you have to build 80% on top of that, that's going to become very difficult for developers. And finally, one thing that is typically on the mind is how can I map my use case into a messaging use case? And if you can make it easier for the developers, so that if I reason in a certain way of I see this as a queuing problem or as a streaming problem, and I can map directly from what I'm thinking as a business problem into a messaging problem, that becomes very easy for a developer to do that architecture, that implementation. Instead, if he has to transform, and if there is an impedance mismatch between the two, then it complicates a lot of things. On the other hand, if you look at Hothan from an organization perspective, there are a few different things that are of a consideration when you're choosing a platform, when you're like investing in a platform, right? And sure, a company will be interested in having that developer productivity, making that developers happy, but they will also have different considerations. So for example, you might want to, if you are an organization, you will have multiple use cases and with different workloads and very different kind of scenarios. And you don't want to have like 10 different platforms, one per each. So you want to standardize on a single platform that can do all of the use cases, or at least most of them, in the best way. And another one that is very important is to encourage a culture of sharing data. If you have a large engineering organization, you have multiple teams doing different components, different services, different sources of data. And having the ability to share data between different teams in an easy way, it is very important. Because otherwise you have data silos and you cannot really unblock the full power of the data you have. If you make it difficult from team A is generating some data and team B has no way easy way to get access to that data in a safe manner. Organizations do also care about cost-effective solution. So when you run at scale, you have different categories of cost, and one is the cost of hardware. So like if you have many use cases, you will need a lot of machines and it will cost a lot of money. So if you can reduce that and consolidate into a single cluster, for example, it becomes very advantageous on the hardware perspective. And the other one is operating costs. So sure, hardware costs money, but it also costs engineering time to maintain. So if you have a cluster, it takes a lot more engineering effort to keep this cluster up and running, to monitor them, to upgrade them, and so on. And fourth and last, the strong guarantees on availability and durability. We've seen that in a lot of these use cases, especially on the operational domain. These are very critical use cases that are in for like mission-critical applications for these companies. And therefore, the guarantees on data durability and availability of the systems becomes more and more important. And sure, some people will say that you don't need to have synced data. Typically, it's the people that don't have a good story on syncing the data on the disk that will tell you that. But that extra level of protection is very important when you can relate to the chances of losing even a small portion of these messages. And if one message is like one user account, someone buying something on your application, then it becomes more and more important. So I want to next go on and show like what we have been doing to make this, to moving into this right direction here, starting from developers. So if you look, and the first part that we have been working in the last 1 year has been around improving non-Java clients. We had already several client SDKs in C++, Go, and Python, Node.js, C# and others, but we kind of like, we were not at feature parity with Java, so Java typically had the latest features, but in these languages we didn't have the latest features. We have worked a lot on improving the stability of these client SDKs, and one of the main friction points was that we didn't have precompiled binaries for, say, Python or Node.js. So now it becomes much easier. You can just do, if you're in Node.js, you can do that, just do npm install. We just download the precompiled binary for your platform. Same with Python, we have all the matrix of possible binaries. So that becomes much more accessible on that front. And finally, one other thing is that the source code for this client SDKs has been split from the main repo. So now we can do much more frequent releases. It is more agile process to have new releases for client SDKs. Another one feature that I really like a lot is the scalable delay delivery. So you can think of delay delivery as a feature that it was introduced in Pulsar 2.4, but essentially you can publish a message and have a delay assigned to this message, or timestamp with an absolute timestamp. It can be used for multiple different reasons. So you can do like a retry operation. Something failed, you can want to retry this operation later, or you can use it as a scheduler of tasks, or more generally like as a distributed cron-like service. Now, the existing implementation that we had since 2.4, it was okay, but it has few limitations. For example, like the index between the timestamp and the message ID was kept in memory. Now, that means that if you have millions and millions of these delayed messages, that ends up using lots of memory. And there's an upper bound there. And the other problem was that this index is kept in memory, and it has to be rebuilt if you move the topic to a different broker. So there's a lot of background reads that will have to happen to rebuild that index. So with PIP 195, there's a new mechanism that is using a bucket system. And now we don't, basically the index does not have to be in memory all at the same time. And we don't need to rebuild that index when we move the topic. So essentially, you can have as many messages in this delayed delivery queue model, and also offer a lot better isolation between different tenants. So since we don't use that much memory, we don't affect other tenants on the same brokers. Another aspect of making developer life easier is what can we do to unlock better architecture for application developers? So a common problem has been, so you have your application and you have to decide how to map your business domain into topics, essentially. And typically you have few different options. Like either I can use one single partition topic for all my users, all my customers, all my resources in a way, right? Or I can use one topic per customer. And people say, okay, which way is better? And there are different reasons to go one route or the other, right? So, but if you look at the one single partition topic, basically everything gets multiplexed into one single topic. Now you have hash-based partitioning, so the same key will go to the same partition, fine. But in this model, basically you don't have visibility on how many events for a single users are on your topic, because everything gets mixed up. Also, you don't have a lot of isolation between noisy neighbors. So if you have user 1 that has X messages, and you have user 2 that has 10X or 100X messages, there's no fairness. So user 1 can be delayed because of the amount of data on user 2. And you cannot apply any fair dispatch logic, say 1 and 1, or you cannot do any rate limiting for customer because you do have that messages piled up there. If you go on the other route, though, you could have one topic per each user. Now, it's kind of like you have now more visibility on what's happening per each of your users, because you can see, okay, how many messages are sending each of them, how many messages I'm backed up on each of them. And you can also say, I want to just replay and scan all the events for a single user, which you couldn't do in the other case. You have isolation, and you can apply either like fair round-robin dispatch, or you can say prioritize one customer versus the other based on different business consideration. So it's a very different model, and but in order to deliver on the promise of this model, you basically like the system needs to be able to work for any number of topics, or at least for a very high number of topics, which is kind of a challenge for infrastructure software, right? So today, Pulsar runs at most like 1 million topics, 1 to 2 million topics. But what we do want to achieve here is to want to go like 10x or 100x supporting in number of topics. That basically will free application developer to not fear that model anymore, and you can have much more simplified architecture because of that. So last year, we have been announcing that we were working on a Zookeeper replacement, and we have announced the release open source earlier this year in April. And so we announced Oxia. So Oxia, essentially, it is a system that we have created in open source to solve metadata coordination problems at a large scale without making any compromising on how much of this data or how much throughput we need to achieve. And it is based on a new architecture that takes advantage of modern cloud environments. So basically, we base on Kubernetes instead of assuming bare metal. And we are announcing today that we have like a private preview of Oxia in SN Cloud. And shifting a bit the gear and looking more on the organization and operational side, I want to go back a bit on the multi-tenancy. So multi-tenancy is really the key to achieve low cost of operation. Like if you have to maintain many clusters, it is very difficult to have low cost of operations because there is a lot of engineering time, a lot of hardware, and so on. But having a single cluster, basically we don't have to provision all the slack capacity for every single use case. We can just basically have it as a shared slack capacity into this single cluster. Also, we don't have to provision for the worst case scenario because we don't have to retain data for assuming that everyone will have an outage today. We can assume that only a fraction of our consumers, our use cases will have, application might have an outage at a given point in time. Now, if they do have all the same time, we can still increase the cluster. Dynamically, it is very easy, but the point there is that we don't have to pay for this extra capacity always, and we can just have some room to accommodate for failures and for people like backing up the data. But the other part is easy access to data. So for easy access to data, there are two parts. One is technical. So if you do have a shared cluster, the data is there, and everyone has connectivity, you just need to open the gate. So you can control with using ACLs and give permission for people to read the data. And it is one click away. The other part is more like a process and organizational problem. So if you think that, OK, team A is generating data, they have their own cluster, they own the cluster, they own the data. Now, if team B goes and say, oh, I want to read that data, and say, oh, by the way, but now I have to expand my capacity, or like I have to give you access there, who is going to, like if team B is doing something bad, my engineers are on the hook. So it becomes a friction point between different teams. So it's like really like an organization problem. But if you switch the model, now if you have a single cluster that is maintained by a single team, now no team owns the data that generates. So, and no application team is on the hook for something that other teams are doing. So it is much easier that, OK, I'm generating data. This is like the feed of events, say, new accounts created for users. Anyone that's interesting can just go in and get access and then consume the data and do stuff on top of it. So it is really like removing that friction point. And Pulsar was really born with multi-tenancy. It was like really the first design goal there. So there is namespacing and tenants concept. There is enforcement of traffic and storage quotas, both at the single topic level or at more like a namespace or tenant level. There is a really
isolation for write and reads, which is really important at the low level to guarantee that someone reading will not impact performance on other people writing. And there's a lot of other tooling like dynamic topic isolation that can be used to move around things when tenants can cause impact on the cluster. And again, tying a bit back on the unified platform, we say, okay, Pulsar unified platform messaging queuing. It is also, we can kind of like build a bit that more on the fact that, yes, we support multiple use cases, but it could be naive to think that we can live in a vacuum, that everything could be migrated to Pulsar in a whim, right? So there are other systems out there and use cases that are out there and using other technologies. And no matter what advantage we can say that Pulsar has, it becomes very difficult sometimes to migrate those use cases. People don't want to change their code for good reason. They have to retest it and use a different API, new models, and then making all that transition. But the reality is that these kind of like applications are going to be there. So if someone has written an application with a certain API, most likely that application will continue its life cycle with that API. And it is fine. The response that we have been giving in Pulsar community has been to, we can support multiple protocols. And actually, I think that Pulsar is kind of like the only platform out there for messaging that is truly multi-protocol. So we do have our own protocol. We do have our own set of features, which is where we can build new innovative features and making things very efficient. But at the same time, you can support out of the box different protocols like Kafka protocol or MQTT or MQP, and basically like making that transition, that migration story very easy for developers. And in a way, you can see that as a migration tool. At the same time, like if you say, okay, I have this application, I want to take advantage of some of the improvement that Pulsar can give in terms of multi-tenancy, in terms of operational improvements and so on. The answer is that you don't have to migrate your application. You can keep using your application. If it was written with Kafka Producer, fine, just keep using that. And it can work very well within Pulsar. And one thing that we have been working on, the team this year, has been KSN, which is Kafka for StreamNative Cloud. Essentially, it is an improved version of KOP that was specifically designed for StreamNative Cloud. And with the new 3.1 version, we have added support for Kafka and Pulsar compaction that work in the same way, and that was kind of like the last step that right now we can support more complex Kafka applications, for example, like K-streams or KSQLDB can work out of the box with KSN. And if you look at the performance, it is really on par with the native protocol performance. So it's really great, and it is now GA in SN Cloud as of today. So, and I also suggest to check out the section from Dustin around using unlocking power of Pulsar for Kafka developers at 1:35 today. Going forward on the compute ecosystem, we have done a lot of work on improving the support for stream computing engines like Spark Streaming and Flink. Right now, we have collaborated with the respective communities, and the support has matured a lot. I also hope you can check the talking session from the data breaks on how we collaborated on the Pulsar Spark integration. And last but not least, Pulsar, we also have Pulsar function, which we can announce that it is now GA in SN Cloud. And we have a lot of upcoming features for Pulsar function as well, from generic runtime to stateful functions and the auto-scaling for the functions instances that's coming up. And last year, we announced that we were working on a streaming SQL support for Pulsar. Again, now this is on public preview. It is not a compute engine. It is not a fully fledged something that can do everything, but it is a very useful tool that can let you do like basic ETL, basic analytics on top of your data that you have already in your Pulsar topic. And talking about autoscaling, we took a lot in the past that Pulsar architecture makes it very easy for us to do autoscaling. Because of this separation between storage and brokers, it means that the brokers have no durable state, and we can basically transfer topic easily from one broker to another without needing to copy any data. That's very different from other systems. So we can scale up the broker, scale it down very easily, and we can do that multiple times a day based on traffic patterns. So the broker part on the autoscaling, it is now in private preview, but we are working as well on getting out the bookkeeper's scalability, both horizontally, adding more nodes, as well as vertically. Like if you're in a cloud environment, the size of the disk as well can be increased when there is more storage or more throughput capacity. And for more announcement and integrations here around Pulsar and Lakehouse. So Pulsar has been working with several of these communities around Lakehouse implementation from Hoodie, Delta Lake, and Iceberg. And we can integrate very well with this with these Lakehouse technologies in two different ways. So the first one is around sync connectors. So if you have your data in a topic, that data can be easily pushed to any Lakehouse system, and then you can run your own batch workloads from there. But one of the most interesting one is to basically integrate this Lakehouse technology at the tier storage level. So at this point, you can basically say that Pulsar can offload data directly into this Lakehouse format using different technology. And then you have two ways of reading this data out. The streaming way, in which basically goes through Pulsar API and the Pulsar broker. But you can also run a batch job, and that does the batch read directly from this tooling with their native APIs. I also want to call out that there's a session about streaming data into your Lakehouse from CG and Yingjun. So please check it out. And again, a few other features that kept us busy in the last year has been around how can we improve how we manage traffic in the Pulsar cluster. And so, as we say, Pulsar brokers have no durable state, so we can move traffic around. It is very easy. But what is typically tricky is how do we make that decision? How do you decide based on the load how to move when to move topics from broker A to broker B? Because the traffic patterns are changing, and the perception that each broker has of orders of the current load is also changing. And so we have basically rewritten the load manager, which is the component that decides the allocation of topics to brokers, to make it more scalable and to have a much fair and distribution, and to be much more quicker in a way that it reaches a stable state. So if you have any imbalance in the traffic across brokers, it will basically now react much more quicker and much more and reach the stable state in a much shorter time. And finally, one other thing that kind of is correlating to this is how can we minimize the amount of time that it takes to move topics from broker to another. Basically minimizing that small unavailability time during that transfer happens. So Hisung is going to do a session on describing the design and implementation of this new load manager at 3:35 today. Another aspect is around telemetry data. So telemetry data, if you look at the amount of metrics that can be produced by a Pulsar cluster with many, many tenants, it can be big, and it can be overwhelming to any TSDB system. Especially like if you want to have very fine-grained visibility on all your topics and so on. So what the team has been working on is like, okay, rehauling the whole way of how we measure things, how we collect the metrics, and how we expose them. So Asaf has done a presentation on the future of metrics and to illustrate the path that we have been following for solving this problem. And finally, I want to go back and have again call out one of the aspects of Pulsar and StreamNative Cloud. So one important part is that is a very flexible deployment model. So we can deploy Pulsar in StreamNative Cloud in many different ways. You can deploy as a hosted service in either GCP or AWS, and we can deploy also as a BYOC, depending on the different needs of that organization will have, but also as a private cloud, self-managed. And the final one is the edge. So we also are able to deploy Pulsar directly at the edge using these microclusters that can perform some computation at the edge directly and do like filtering, analytics, or even like using machine learning model as within the Pulsar function framework, and do all this anomaly detection and filtering at the edge, and then propagating back to cloud only the relevant alerts or relevant information. And so today we can announce that private cloud is now GA, and there is also a private cloud free trial that you can go and is completely free. So you can use all the same tooling that we use in SN Cloud in a self-managed way for free. So this concludes this session, and I hope you have a fun day today and a lot of learnings with all the sessions and all the speakers. And I'll let you to the next one. Thank you.
How do you? Which one do you? Hello? The slide was. They will post it. Hello, check. Okay. Okay. Good morning, everybody. Welcome to Pulsar Summit 2023. My name is Chandra Ganguly. I'm the Senior Director for Engineering at Cisco's IoT Control Center. Today with me is my colleague and the Principal Engineer, Alec Hothan. Both of us will talk about how we have taken Pulsar from working with StreamNative team and into our IoT control center. So what I will do is I will give you a brief background of what Cisco's IoT control center is all about, and Alec will dive deep into how we've taken Pulsar and then include it into a brownfield cloud and SaaS offering, and explain some of the challenges as well as where we are in this journey. So what exactly is Cisco's IoT control center? It really is device lifecycle management of any IoT device. So what are IoT devices? It can be a connected car, it can be a PG&E meter, it can be a utility meter, it can be your alarm systems. So for example, if any one of you were driving a Ford, GM, BMW or a Tesla and coming over to this conference, guess what? That car was always connected over a network. You may not know it, you may not have paid for it, but that device lifecycle management of the car throughout its journey back to the parking garage here was managed by either Cisco's IoT control center or a similar platform. So what we do is we do a full lifecycle management of that. So not only do we provide network connectivity, we also think about that we work with SPs and enterprises from the network to also provide the billing associated to that, because the card is always sending some data back into the mothership, in that case with respect to enterprise motherships. So there's always some data going back and forth, hence there's usage of the network. So we have a billing associated to which is, so every account has a rate plan and a comp plan, which basically maps to how much how much they will get charged at the end of the month. Not only do we do that, we also on a daily, weekly and monthly basis, on a per account basis, we also send reports about various kinds of usage that the device is going through. And what enterprises and SPs do is they write their own engine on top of that, OnStar as an example, and essentially have their own dashboard for their use cases. The platform also has a very rich UI and an API, and there's almost a second order of business that is going on where the enterprise subcontracts it within their IT department or another contractor who will write a complete dashboard for their use case, for their monitoring systems and whatnot using that API. We'll talk a little bit more about how intense that API API calls to our platform is as we go through this presentation. So before we go into a little bit technical aspect of it, let's talk about what is the ecosystem this particular platform called Cisco's IoT Control Center actually plays it. It is a market leader. How is this laid out? It's a SaaS offering. It's a multi-tenant SaaS offering operated today in private data centers. And it's basically, we have 17 deployments worldwide. They're geo-replicated. So in case one of the physical data center physically goes down, we still have connectivity both from a data and control point of view. We work with about 35 plus SPs worldwide. They in turn work with 35,000 enterprises. And obviously it's impossible to list all of them, but listed, you can see on the very right side, flavor of the kind of enterprises we work with. Today, across the 17 deployments, we have about 245 million and growing number of devices today available. Of those 245 million, about 84 million are connected car. It's one of our biggest and fastest growing business line. We are organically growing, just with the current services, we have about 2 million devices per month. It's a 20% growth rate that we have today. And what I was talking about is the APIs. On an average, we have about 4.5 billion APIs a month call. So obviously we have to have throttling and other technologies on this platform so that nobody has a runs over or has a pseudo DOS attack because they just went through, had a much larger rate of API call than what was in the SLA. So let's dive a little bit deeper into what the architecture of this platform is. So I will break this up into three pieces. On the very right, you have devices connected over wireless network as IoT, as most IoT devices connect through. We have an offering where Cisco manages the wireless network, or the customer can manage the wireless network. In the case of one of our biggest customer, we do it. So there's a peer team next to the engineering team. This is the wireless networking team. They and the platform services work together to manage that on a 24/7 basis. We also have customers who have decided to run their own packet gateway. Part of it is their preference, part of it is because the packet gateway needs to reside closer to where the customer devices are, just because of latency. Otherwise, we will backhaul everything into where our data center is, where we host the packet gateway. So that's called a V2 model. We in those cases write adapters which can talk to their packet gateways. So that's the very right. The packet comes in, the whole design is done in such a way that the data and the control planes are separated. So in case the cloud goes down for whatever reason, just by the geo-redundancy design that we have, the data plane can continue to work. So devices cannot lose connectivity. That's what our golden path is, no matter what. That is the theory at which we, design at which we have. On the very top, you see customers interfacing with the platform through their API or UI. Now, when the packet comes in, basically this packet is called CDRs, or call data records. Essentially, we take a copy of it, send it to the control center, and that gets pre-processed, and Alec will talk about all the details of how that gets processed. And at the end, it will be in some kind of data store, whether it's an Oracle or a Mongo or a Hadoop data store. And think about it, all the systems that we have over 300 applications running in each instance of this pod. There is a pub/sub model. There is a publication, and there is something, there's some applications are publishing, some applications are subscribing to those messages, consuming and doing next set of work. So now, hence comes the messaging broker. So as you see in the very bottom, there is a messaging broker there. So far we were running with a Christle, which is a very legacy messaging broker, has some limitations. So that is where we are replacing that with Pulsar. So that is why what is relevant to this conference and the context of this deployment. We also have, along with CDRs, we also support very, very low end like agricultural devices and all, which only sends 1 CDR per day per month. We also have a very low end called CC Lite, where the usage is not something we have to manage on a daily basis, or well, we have to manage on, but once a day or twice a day, not on a continuous basis, as is most connected devices that you see here. So what's the modernization proposition here? So what we see on a daily basis is the device count and density growing up. From the customer point of view, the cost per device has to come down. Every time we renegotiate a contract, there's always this pull and push about the cost. But the customer's expectation of the experience and the service that we offer has to always move up the chain. That's really the thing. So essentially what we are solving for is the device lifecycle management. We are seeing a continuous rapid growth of connected devices. Obviously, connected car will be the primary one. Any of the CDRs that comes into our data center, there is based on the kind of profiles we have, our comp plans, there's always an automation rule that gets triggered. So for example, if a particular account has a usage limit, and if it moves above, we have to obviously move the rate plan and the communication plan associated to that. So those are called automation rules. We triggered about 2 million automation rules every 2 minutes. So that's the kind, think about it, we have 245 million devices. So it's not much in terms of the relative numbers, but in terms of scale, that is the kind of scale we have to adhere to today, and we expect this to keep on growing. So we have almost near real-time redundant system, geo-replicated. Security, because we are operating this as a SaaS, Alec will talk about it, we release every 3 weeks, but the security in the PCOs associated with that has to be 100% kosher. And we need we have some clouds, depending on customers. We also need to operate them in an air-gapped manner. So it's a private data center in an air-gapped manner. So you essentially get, have another set of challenges that we need to work through. All of this for today's summit and relevance is the fact that we need a messaging system, which has to be reliable, which has to be scalable, extremely light overhead. What we are investing today is such that we are investing for the future. And essentially it has to be geo-replicated. Everything in that messaging system is secured, encrypted. We have to have a mechanism for rotation of passwords and keys and all of that. And it needs to work with other messaging systems. Remember, we talked about a model where we talk to the customer network. That can be running on, their HLRs can be running on Kafka, and we need to talk to Kafka. So this can be other, that's extremely important. And the last but not the least, it has to be recovered from any disaster. Remember, we are in a geo-replicated system. Once one data center goes down, the other picks up. But when this comes back up, everything has to sync back up. So that's the high level context and background of the platform in which we are getting into Pulsar or deploying Pulsar right now. And with that, I will hand over the rest of the presentation to Alec, who will give you a little bit of a flavor of what what the technical details associated with this deployment is.
Yes, thank you, Chandra.
Yeah.
Okay, check. You hear me?
Thank you.
Yeah, so in this second part, I'm going to focus more about what we do with Pulsar, how we use it, and type of workload that we run with Pulsar, and also some information about how we deploy Pulsar and how it integrates into our CI/CD system. This first diagram here to show you typical applications that we use Pulsar with. And so the typical pipeline, you see a lot of records like CDRs coming into this pipeline. And the types of CDRs, they can vary based on different operators might have different formats. So they can come in CSV format or even a binary ASN.1. So this first level of ingestion is really about extracting these information and then put them in the first stage of the pipeline, which is the first it's a Pulsar topic there. Right? And then the next stage will more normalize this, and in our case, we use protocol buffer to normalize everything. And the choice of protocol buffer is really because of better efficiency for encoding and decoding. And it also yields a much smaller size for messages. Right? So it used to be JSON, and JSON is very slow, right, for decoding and coding. And size of messages with JSON was over 1 kilobyte, 2 kilobytes per message. And with protobuf, we could reduce this to around 400 bytes. Right? So big gain there in terms of message rate. Right? And then you have multiple stages like this. On the next stage, we'll have deduplication because we don't want to process the same CDR records twice. Right? So sometimes operators, they send multiple times the same CDRs by mistake. Right? And this is actually a pretty challenging stage because we have to keep a history of about 1 month worth of CDRs, which can amount to tens of billions of CDRs. Right? So that's a pretty intensive application there. And then the next stage will be about rating the CDR, meaning we associate a rate plan to each CDR, and then we add a lot more additional properties to the CDRs. Right? And then after that, you have additional stages to do rule automation. For example, if the usage passes a certain threshold, we have to change the rate plan. And then it ends up into a big database. Right? So that's kind of one example of pipeline we use for. And there are multiple different pipelines, different types of messages. And what's really important for us is a streaming platform that can handle variations in loads and spikes of traffic. Right? So the traffic is kind of not very, it's kind of predictable. Right? And as you can see, you heard about having cycles like depending on the time of the day. In morning time, traffic goes up, and then evening it goes down. And even the week of the day, day of the week, on weekdays, it's a lot more busy than weekends, right? So there's variations of traffic, and it needs to absorb not only these variations, but also unexpected spikes coming from the network, right? And in terms of rate, so the smaller data centers, they have maybe a few million devices. And in these cases, we have ingestion rate of around up to a few thousand messages per second. Right? And on the largest data centers, they might have tens of millions of devices. And there the ingestion rate is about 10 times this. So about up to 10,000 events per second. Right? So in terms of Pulsar, we use one Pulsar cluster to manage all these topics in these pipelines, other pipelines as well. And the sizing of this Pulsar cluster, it really depends on the expected income rate for all these messages. Right? And just for reference, the smaller Pulsar cluster we deploy, they are sized to support around 50,000 messages per second aggregate, counting all the topics. And then the larger size is about 10 times this, which is about 500,000 messages per second. In terms of redundancy, so we have pairs of data centers that are always connected to each other. And we deploy one Pulsar cluster for each data center. Right? And in this case, they are connected using geo-replication. So we have some of the topics are geo-replicated. And some others, in terms of retention, we do have a small retention time. Like, for example, some topics have 2-week retention. And that's used for engineering to troubleshoot. If we have problems, we can go back in time in 2 weeks, up to two weeks ago, and then replay the messages to see what happened. Right? So, and we have also topics that are long-term, like multiple months. And those topics can contain a really large amount of records, tens of millions of them. Right? So in terms of updates, software update, the cycle that we use is every 3 weeks. We have software updates. And applications usually update every 3 weeks. And Pulsar is the same way. We can update Pulsar every 3 weeks. And this kind of application, the incoming traffic is nonstop. Right? So we don't interrupt traffic. So we have to do all the upgrades without impacting service. So that was one of the big challenges when you have a lot of traffic coming in. You have to make sure that when you update, application restarts, you don't lose messages in this process. Right? So in terms of scale, we have each of these stages can scale out individually. Right? That's how we have to cope with peak of traffic. Right? And Pulsar itself, we kind of dimension it to make sure that we handle the maximum load in a comfortable way. Right? So we don't want to get very close to the limit there. And right now, for example, in production, we have several clusters deployed, and they are currently at about 10 to 20% capacity. Right? So there's a huge room that we have to handle any spikes. And same in terms of storage, we make sure that we have sufficient storage to handle any backlogs there. The applications that we have are mostly Java applications, mostly migrating from existing code. And some of the apps are also Go clients for those that are more performance sensitive. In terms of, we talk about failovers too. So every 3 months, the applications they're running on one data center. And the other side, they are just standby. Right? So, and then every 3 months, we try to fail over all the activity to the other data center. And in terms of Pulsar, Pulsar does really run active on all sides. It's just that on the non-live side, the Pulsar is a lot less busy. It's just busy about handling geo-replication. So that's pretty much what it does there. We're going to now look at the deployment part of Pulsar, because that's something that we really spend time. About 2 years ago, we started this journey about how to deploy Pulsar in production on Kubernetes. When you get a Pulsar from open source, there's some documentation explaining how to deploy it, but there's still a lot of unknown for people who do this the first time. And for us, that was certainly a big learning experience. And what we can say now is that there's really, there's really 4 areas that you need to interface Pulsar deployments. They are related to storage, to the networking, to observability, and to the security. Right? So all of our deployments on Kubernetes are using Flux CD. And Flux CD is an open source continuous deployment project from CNCF. And we select this one because it was pretty easy to set up and very flexible. Right? And the way Flux works is that every cluster that you want to deploy to, you deploy a set of Flux controllers. Right? And these controllers, they will be in charge of reconciling the state of your cluster with the state that's described in the Git repository. Right? So you basically have a Git repository containing the description of all your workload. And then the Flux controllers are going to pull that repository. And then if it sees that there's a missing Helm chart or there's a Helm chart that has been updated, it will take care of triggering that update for you. And so Pulsar itself, we use the Pulsar operator to deploy Pulsar on Kubernetes. And it works pretty well with Flux because it's a declarative way to deploy your cluster. You just have a manifest file or custom resource where you describe how many bookies, brokers you want to deploy. And the operator will be responsible for creating the resources for you. And the other operator that we use, which is pretty recent, is the Pulsar resource operator. And we use this one to create other resources such as Pulsar tenants, namespaces, topics, if you need to create them ahead of time, and then also the geo-replication connections. Right? So those also work pretty well with Git-based deployment, because then you can just describe your resources in the Git repository, version them, and you don't need to write any script to have to create them, for example. In terms of observability, right? So you know that Pulsar comes with options to deploy Prometheus and Grafana. Right? So in our case, we don't use these options because we have policy to send all of the logs and metrics to a central location. In our case, we send them to the cloud, and in our case, we disable the Prometheus and Grafana option. And then we make sure that all the logs and metrics from Pulsar, they go direct to the cloud. Right? So for us, it's a much better solution because we have to manage dozens of clusters. Right? And that really gives us a single pane of glass to see all of our Pulsar clusters in using one location. So that works pretty well. And in terms of observability, I think Pulsar is pretty complete, right, in terms of metrics and logs. And from that point of view, we have a lot more metrics than we can use there. Other areas is related to the storage, right? Because that will drive directly the performance of your Pulsar cluster. And in our case, we have 2 options of deployments. And the first one is based on local storage. So that will give the best performance, best latency, but at the expense of flexibility. Right? So if you have a storage drive that goes down, you lose totally the content. Right? So, and it's harder to add additional nodes because you need to procure for the hardware. Right? So better performance, but not as flexible. Right? The other option is to use network attached storage. Right? In our case, this is the easier for us because in all of our data centers, we have already NetApp storage in place. And with that, for us, it's very easy to deploy a new Pulsar cluster using NetApp data storage. And the downside of this, of course, is you're not going to have something as performant, right? But in many of our use cases, the performance numbers we get with attached storage is still good enough. So in terms of security, we deploy with Istio, and Istio is a service mesh. And Pulsar operator supports Istio as an option where you can enable Istio. And this option actually doesn't really deploy Istio for you. It just helps set up the configuration of the Istio ingress gateway for accessing Pulsar behind this gateway. So it's still up to you to deploy the Istio service mesh and control plane yourself, right? And on that front, deploying Istio can be simple or very complex, depending on the deployment model that you use, right? And in our case, we decided to use a simpler model where the Istio control plane is deployed in the same clusters as Pulsar, right? And we only use a single service mesh that will, where we will deploy Pulsar in it, right? And in cases where we have applications that use Pulsar that run on the same Pulsar cluster, same Kubernetes cluster, we also put these applications in the same service mesh, right? So, and that way, these apps, when they talk to Pulsar, they don't have to go through the ingress gateway, and they talk directly to the Pulsar brokers, right? And all of these communication between apps, brokers, and broker cookies, they are secure using service mesh, and they are all using MTLS in our case, right? And for external applications that need to connect to Pulsar, they have to go to the Istio ingress gateway, and we will be using TLS in that case, right? For authentication, we have decided to use JWT tokens. And so there will be a talk later today about all the security configuration of Pulsar. And so I'm not going to spend too much time there. I'm just going to say that the part of trying to design the security settings for Pulsar, that's what took us the most time, because you need to take into account a lot of different things, like where do you store secrets, what's the public key infrastructure that you have to connect to, and then you have to also reconcile with the security policy in your organization, and then also make trade-offs based on what your ops teams can handle in terms of operations on all the keys and rotation and such. One important point for us too is being able to update Pulsar very quickly, right? So these kind of infra services used to be upgraded or updated very infrequently, right? Only when you have a bug to fix or you need a feature. But today, the upgrade cycle for these services is a lot more frequent because of security vulnerabilities, right? So Pulsar is an open source software which has a lot of libraries, right? And so it's very important to make sure that these libraries don't contain unknown security vulnerabilities, right? And that will often result in the need to update Pulsar a lot more frequently than you would need, right? And so that's a big change. And for us to achieve this pace of update, it was really important to integrate Pulsar into the way that we build and deploy any other application in our data centers, right? So the first thing that we do is that when we have a new version of Pulsar to integrate, we import it into our Git repositories, right? And we use a tool for that. And the tool will basically check all the container images that are in these Pulsar Helm charts, right? And it will copy these container images into an internal registry, right? And that way, when we deploy them, we never have to go to the internet to deploy these images, right? And the second thing that this tool does is it will modify the Helm chart so that when you deploy the Helm chart, it's going to refer to the internal version of these images and not to the external version of this image, right? And once it's imported, then the CI build kicks in, and that's where we rebuild the Helm chart. And then we put it into an internal Helm repository, and then that will be following the same workflow as any other Helm chart, any other open source Helm chart or internally developed application, right? So, and that kind of workflow that allows us to do really very frequent updates of Pulsar with minimal effort, right? So I'm going to skip the part that describes how we manage all these different deployments. That's more like a Flux, but we have a small number of Git repositories that kind of describe what the typical blueprints of deployments and how we handle the configuration for these different deployments. Learnings from these 2 years of using Pulsar, it's really from day to day, having to update the Pulsar multiple times. So this combination of using Pulsar operators with something like Flux works really well for us. And that allows us to do really painless updates, right? For example, a new update of Pulsar, we can get it deployed on any clusters within half an hour by importing it. So pretty fast there. And in terms of production, we saw that for several months in production was very reliable. We had cases where we have spikes of traffic, the backlog went up, and then it recovered, the backlog was cleared pretty well. And performance-wise, the deployments based on attached storage, they were pretty good as well. Right? So areas that need improvement are more related to the scanning of Pulsar hand charts, right? So every new version of Pulsar brings in new versions of code, right? And that's something that we need the community to really follow very closely and make sure that when you have a new update of a new version of Pulsar, it doesn't regress. And there's a plan to fix all the high security vulnerabilities. Other areas in production, the most important points that you have to monitor are really backlogs and resources like disk usage. Right? And for that, once you have alerts in place, it's pretty much uneventful to manage this, very low maintenance, let's say. And the last part for updates, when you use operators, you have custom resources, and the CRDs, when they are not versioned properly from version to version, then that forces you to do certain things before and after the updates. Right? And those things that can be really, I think, improved for the next releases. And looking forward, we're looking at scaling these platforms. Like you see, the traffic will increase every month, and we're looking at scaling this and having a means to auto-scale Pulsar is really very interesting for us, because that means we don't have to continuously follow how many instances of rookies and brokers we have to deploy. Right? So something like this would be really interesting. And then in terms of apps, looking at transactions and functions, which are fairly new, and we're just waiting for these features to be more mature, and then give it a try. Right? In terms of performance and Istio, so one of the issues often mentioned for Istio is that it does introduce some overhead performance, right? So because with Service Mesh, you have a sidecar that is inserted in every pod, and then you have extra hops, right, for connectivity. And for those, there's a new version of Istio that came up recently that provides the same mesh without the overhead of a sidecar. So this is something I think that we will be trying soon on Pulsar. And configuration management is also a challenge. I think any continuous deployment system you use, that will be the most complex part. Like how do you manage complex configuration when you have a lot of clusters and different types of deployments. Yeah. I think that's pretty much it. And so if you have questions, we can take a few questions.
Thank you.
Thank you so much.
I think you have a question.
Oh, you've got questions?
Tiered storage. Yeah, we're not using them right now, but I think we will have to use it, especially in the case of deployments using local storage, right? So local storage, we will be having NVMe drives, and so the size of the storage is limited, right? So you cannot store too much information, right? And the plan for us is really to reserve local storage for topics that don't have a lot of retention, right? And those that have longer retention, we're planning to offload them to not-touch storage, which is much cheaper. Right?
Thank you.
Excellent. A huge thank you to Alec and Chandra. That was an awesome talk. I really appreciate it. And I wanted to welcome on stage David Christle, who's going to be talking about machine learning with Flink, Pulsar, and Iceberg. Go for it.
All right. Yeah, so thank you for coming to my talk and for the warm introduction. It's a pleasure to be here at the Pulsar Summit to tell you about some of the work that we've been doing at Discord for about the last 1.5 years, taking Flink, combining it with Pulsar and Iceberg to build a real-time streaming machine learning platform. In this talk, I'm going to kind of set the tone for machine learning and why it has a little bit of different requirements than what you have in other event-driven applications. And then I'm going to deep dive into some of the technical choices that we made when we were building this system that address those kinds of specific needs for machine learning. But the essence of this talk is not necessarily about the individual technologies, but about how I think that we've come to a point in the maturity of these technologies and the connections between them, this kind of ecosystem around them, that what now exists can be used to build something that is really powerful and useful purely based on open source technologies, even with a very small set of engineers that built the work that you are about to see. So hopefully whether you are kind of a veteran in the streaming world or you're kind of curious or new to machine learning, there's something in this talk for everybody. So a little bit about me. My name is David Christle, like I was introduced, and I'm currently working at Discord for the last 1.5 years on the applied machine learning team. Now our team is largely split into 2 focus areas, safety and personalization. Most of my work and the kind of prototype system that we built here is oriented for safety machine learning, or sometimes called anti-abuse machine learning. So I have about 6 years of experience in this space, previously at LinkedIn and Cash App, and seen the whole kind of gamut of problems that you have to try to tackle with machine learning. And what this means is that we're operating at a very large scale. So this is not just a question of like, oh, we want to detect a few fake accounts. We're operating at the scale of like millions of accounts, and we have to deal with bot attacks, very spiky, unexpected traffic. And we're also operating like platform-wide and in kind of multiple facets of the products. My background is actually in experimental physics. My PhD was in quantum computing, so I used to work with lasers, microwaves, cryogenics, did lots of experiments, and along the way learned some very advanced statistical techniques, and that's how I got into this line of work, which is quite a bit of fun. So this is the agenda for the talk. I'm going to talk about Discord, what it is, and motivate why people are generally interested in real-time streaming generally, and then also certain applications at Discord. And I'm also going to talk about some Discord-specific infrastructure pains in terms of using machine learning that this platform is going to help us address. We selected Apache Flink for this platform that we built, and I'll describe why we think Flink is a real clear leader in this space. It's especially mature, and the integrations with things are really nice. We're going to talk about the 2 fundamental technologies, Pulsar, which we use for serving real-time events, and why it's really great if you're going to use Flink. And then we're going to talk about Iceberg, which you may be a little less familiar with. This is a cloud storage format that effectively lets you make a very large data lakehouse that is streaming friendly. And finally, we're going to put it all end-to-end at the end of the talk, where we're taking raw data, we're able to make sophisticated features, have an ML model inside the streaming job, and output the scores, and kind of what we did to make the developer experience in using this system really, really solid. All right. So first, what is Discord? It is a real-time video communication platform for hanging out via text or voice or video channels. And that can be whether it's one-on-one. You can be in very small servers with just a few people. These are kind of small groups. It can be slightly larger communities, or it can be servers and communities that have millions of people within them. It started in 2015. It was originally very popular in the gaming community, but it's expanded into a number of other communities ever since then and continues to grow. Like I mentioned, users can join multiple servers. And we have about 150 million monthly active users spread across 9 million monthly active servers. So safety, which I mentioned, which is that kind of one element of our ML teams, has a large focus on combating spam. So that's minimizing users' exposure to spam, spammers, spam content. We have significant efforts in kind of cross-functional teams that are all working to build the infra and address this problem in various ways. Another area is we think about account security. So we want to protect Discord users' accounts from being compromised as proactively as possible. and we also want to detect that as fast as possible if it does end up happening. So an important point in this space that I'm hoping I'm conveying is that the speed and the scalability of what we build really matters. And the same is true for personalization efforts. Like you could think about helping users discover new servers or figuring out what the right type of notification to send them is as fast as possible so that they can see the content that may not be relevant in just a few minutes later. And so we're starting to think about those applications, but most of the focus here is on these kind of safety applications. So stepping back just into like general areas of stateful stream processing that are interesting. It has a bunch of applications. These event-driven architectures are a bit different from traditional architectures using like relational databases. Here, these applications consume kind of a continuous flow of events, and they perform real-time computations and state updates. They tend to be very scalable due to that asynchronous nature. And you can think about building a lot of different tools that are people would consider event-driven. Like you could build a rules engine to detect fraud if you wanted to. You could do business process monitoring. There's another area of application that's very popular in analytics. So analytics, you are taking typically batch queries that you've been working with maybe for a long time, and you're trying to make those as close to real time as possible. So instead of a kind of single output, what you get is a continuously updating view of the result of a SQL query, even if it contains very complex logic. So crucially for our focus today, it's going to be on using it for kind of data and ML pipelines. These frameworks are so powerful, they let you filter, transform, join, aggregate. You have so much freedom in how you manipulate the data, and it works very efficiently even at real time. And so these pipelines, again, can be very simple, something like event ingestion and deduplication. You can do ETL tasks with them. And for us, we're going to try and kind of combine a bunch of these things all together in one application so that we can do ML on streaming data with pretty low latency. So there are particular elements of ML that make it a bit different from other workflows, and it means that our developers need to iterate quickly. First, even if you have a rigorous understanding of the model, the data, you're very familiar with it, you don't really know if this new feature or this new model or change is actually going to improve your solution to your business problem. When it comes to gauging the quality of these models, it's hard to understand them. The interpretability is really tough. The final arbiter is working with offline metrics and saying, oh, well, how would this have performed in the past? Or the ultimate one is to put it online and do a randomized controlled experiment and look at the way that the metrics change. That's really the end, end decision maker. So this leads me to the third point, that even when you're building these things, you're making improvements, you may find bugs, you need to be able to iterate, and each one of those means that you need to go and potentially recompute data in the past. So you need to make that kind of as fast as possible. And lastly, when it comes to tooling, the ML space generally has a ton of tools, and so you want some kind of a pathway to integrate that. So if you're using a language like Java or Python, that's great because you have access to a lot of libraries that you can use for ML. Okay, so now we're going to get into the technical parts. So for responding to abuse, Discord's existing infrastructure for safety, it looks like this. In the bottom is our kind of core rules engine. And it was originally designed for making heuristics. So these are human-developed rules that use kind of raw signals, and then you try to combine them together to say, this is a signal that we want to detect and respond to. So it's originally designed for that and not necessarily for machine learning. And now we want to use machine learning to improve our performance to keep Discord users safe. So this rules engine, it primarily only lets you use data that are within the event. So this is a stateless transformation. You can't really remember historical events in an easy way. We do have separate microservices for things like counters, but even computing an average in this system is hard to do. So coming from a batch world, you're pretty limited. The other thing is, just like a regular microservice, when you deploy it, that's your code change. If I make a feature today, I need to have historical data. Well, I can log that forward, but if this model requires months of training data, I can't wait a month to start using this feature that I built. I mean, imagine if you had a bug in it, and now you're like, oh, I guess I have to start all over. So that's kind of, it doesn't really make sense. In the upper left, we use a batch data engine, so we use BigQuery, and it has access to production dumps, and it has access to analytics events, and this rules engine doesn't, so that's another kind of pain point where we don't have access to all the data that we want to use. Analytics events are typically used for when we launch a new feature, understanding if we've actually enhanced Discord users' experience on the product. But we don't have access to those in the safety system other than through this batch pathway. So what batch gets right is you have a ton of flexibility. You can join all these data sources together and make it as complicated as you want, but the problem is that it's fundamentally just slow. It's always going to be delayed, either by the time the engine takes, how fast the data gets ingested. All of this stuff adds to delay. The other thing is that even when you get the data in there, you have to stitch it together with these kind of real-time features, and that's kind of bug-prone. There's no error message or stack trace that's thrown when you make a bug in a machine learning model. It's like your model just kind of performs worse, but there's all sorts of reasons why that could be, and so it's very hard to debug these issues. It would be great if you just designed your system in a way to try to avoid those bugs from ever coming up, and streaming kind of helps us do that. And then lastly, we kind of create this separate microservice too for each model. Like, it works for us, and it's actually great in this architecture, but it does add complexity. So even if we're just taking in some features, using a model to compute a score and output it, that's like a whole nother separate service. It would be nice if we could kind of simplify that infrastructure. And again, I think the speed thing is really important, and the flexibility, because attackers adapt, they're very fast, so we have to kind of keep up with them and move as fast as we can. All right, so Apache Flink. This is the technology that we chose to be our kind of core stream processing engine. And we had a number of requirements that we're very interested in. So we want a framework for ML engineers to do stream processing, to do very sophisticated transformations. We don't want them to be kind of locked into something that's either too simple and doesn't allow them to have low-level control, but we also do want them to have these high-level APIs so that they're able to do their jobs efficiently and express complex transformations as easily as possible. It needs backfilling support. I think that's like one of the very distinguishing things about ML is we have to be able to go back in time and compute what the feature was months or even a year ago, and that needs to happen within hours or whatever. As long as you make that as fast as possible, that's the right direction. It needs to be production ready, popular, scalable. We want to use something popular because it means hopefully a lot of the bugs have been taken out and a lot of the things around the core engine have been fleshed out. And I think that's one area where Flink really shines. Fault tolerance, observability, debugging, all of those things are pretty non-negotiable at our scale. We can't tolerate a lot of downtime. And we also kind of want to unify data sources, so having connectors to other external data systems is important to us. So we did select Flink, and it has a number of really great capabilities. The first is that it has unified batch and streaming. So what this means is I can write a feature and it operates in an identical way whether you're operating in streaming mode or you're doing a backfill in batch mode, and you don't have to change the code or have two separate implementations. It all works kind of the same way. So that's really good for reducing bugs and improving productivity. It has a rich set of APIs all the way from SQL down into process functions, which expose streaming primitives. I'll talk about that in the next slide. And it's proven at scale. There are massive tech giants running thousands of jobs in production at Flink. We don't have to worry about that. One of the biggest points is the vibrant community. It's one of the most active Apache mailing lists. There are tons of Stack Overflow questions that you can find. You can find presentations of people actually building something with this system. And I think when you're an engineer or you're even just trying to think about what can you build, it's super important to have something out there that you can look at and give you all sorts of ideas to see what is really possible in practice. It has good connector support for both Pulsar and Iceberg. I'll focus on that later in the talk. And it uses Java, which gives us access to a lot of libraries, but has a Python API. That's also a very popular language within Discord. As I mentioned, Flink offers different APIs. These APIs let you, as an engineer, choose the right level of abstraction for your problem. At the top, the highest level of abstraction is Flink SQL. You can literally write a SQL statement on a stream and get the output. Then there's the table API, which is very similar to the SQL one. It's a little bit more composable. It can be more intuitive in some cases. And then you start to get into the data stream API, which is more of a MapReduce style framework, or something if you're familiar with like data frames and Spark. It's a little bit kind of like that. At the lowest level, you can use what's called the process function. So here, you start to get exposed to streaming primitives that are related to time. So processing time, event time, timers. You can write custom Java code to manipulate the internal state directly. And for what we do, where we're interested in being able to make speed and accuracy trade-offs, this is really critical for us. So we wouldn't want just the highest level APIs. And the other cool thing that I'll mention too is that in all of our applications, we essentially use like all 4 of the APIs. You don't have to like pick one when you start the job and then you're locked into that for the rest of your job. You can switch between them. So I think that's another kind of unique feature of Flink. It lets you kind of get that custom control when needed, but not have to sacrifice anything. So going further in the theme of flexibility of Flink, so especially for low latency applications like anti-abuse, risk, fraud, any of that kind of stuff, Flink offers you fine control when needed over time. So there's 2 time concepts in streaming. There's processing time, that's the time that you get the event inside your application, and then there's event time, which is like when the event actually happens. So that was some time ago before it reaches your system, and it can even be out of order in that. It can even get an out of orderness before it gets to you. So to explain why this is important, on the bottom, we see the stream of events that are coming into our streaming operator with timestamps. And at the top is a set of 10-second long count windows, and they update every 5 seconds. And they're, for example, keyed by users. This is basically group by and count of an event on a stream. As events come in, they are placed inside of these appropriate windows. And Flink will do this automatically. And some events are part of multiple count windows. Flink has this concept of a watermark, which is really important. It was popularized by the data flow model originally from Google, which Flink implements. And it is a special kind of event. And it's basically a timestamp. If it's a timestamp of 10 seconds, it says, I have received all of the events up to this point. And so if there's anything that depends on that, I know that I will have an accurate result. I could have chosen to just process the events as fast as possible, but then I would have inaccurate results. And so you can kind of pick what you want to do within Flink. And so you can see, like, if these other kind of events come in and you had said, I'm done with what I want to do at 20 seconds, you may have missed some of the events that would have come later due to kind of inherent out of orderness in your system. So I know this is a bit technical, but it really matters for having accurate results. And that brings us into Pulsar. So as I mentioned, we're migrating to Pulsar, and we have kind of integrated Pulsar and Iceberg together, but we didn't originally start this way. We started using Google Cloud's PubSub technology because this serves the majority of Discord's internal event traffic. Many of Discord's existing use cases are very well served by PubSub, and typically those are use cases that don't care about time. They are wide fan-out work queues. You want to dump a bunch of items onto a queue, and you want to have a large number of workers just process those. And you are totally okay in most cases with at least once delivery. All the stuff that you're trying to do is mostly stateless. But it necessitated a change once we actually built a prototype and put stuff in production using this system. So one thing that we found is the Flink PubSub connector, it receives very little maintenance. It doesn't have the unified batch and stream API. We've had to use like an open pull request in order to make that happen. It has a very, very high watermark lag. So this is like 20 to 40 seconds in some cases. And this watermark, again, is like what you use to make sure that your results are accurate. And you don't need it all the time, but ideally you want the lag to be as low as possible. And you can't really do that in this system. This becomes especially problematic when things get backed up, and that causes a lot of real headaches when people are trying to deploy this, and we don't want that experience for our developers. And it has some missing features like transactions, and the cost also becomes high at a certain scale. So the right approach is actually to change to a different technology. So with Pulsar, this is Pulsar Conference, so we all know that this is a scalable, kind of production-ready system. The key for us is that it not only has that queue delivery mode, which is very, very popular in Discord, but it also has this partition-style delivery mode. And if you look in the lower right, the idea is that these partitions have a time ordering guarantee on them that queues don't, and we take advantage of that to have a very short watermark kind of experience. And so that's how we can get accurate results with low latency. It has this disaggregated storage and compute, makes scaling easy. There are managed solutions like through StreamNative, so we don't have to think about infrastructure as much as we would otherwise have to. And it supports Java, Python, and Rust, which are popular languages within Discord. I think the Flink Pulsar connector deserves a special mention because it has this unified batch source and sync. It's actively maintained. It was originally developed by StreamNative and then donated. You can do SQL directly on streams. It's really great. And all of the extras are also in the connector. So these connectors are not particularly easy to write. They map Flink's fault tolerance model onto the external data system that you're working with. So you have to kind of know the ins and outs of both of them in order to write these. We have a very small team. We are not in the business of connector maintenance, so it's great to have something that's powerful and just works really well out of the box. So this is kind of the infrastructure that we are building. The new stuff is in blue, the existing stuff is in black, and that's kind of a separate part of the company. And so what we're doing to kind of migrate is we take a tap off of this validation service, which is an existing service that has these analytics events. We put that into a buffer, and then we do some schema translation and encoding, and put those on separate Pulsar topics, which is way more organized than having all your events on a single topic, which makes it kind of hard and kind of expensive to deal with. We're taking the safety events, and then we're restreaming those also into a Pulsar topic. And the goal here is that our engineers can build any kind of application, select any event that they want. This architecture is also simpler for doing access control in a cleaner, more kind of observable way. And we're switching to things like protobufs so that our serialization is much faster, more efficient, and our developers have strong type safety. All right, and so historical events and backfilling with Iceberg. So far, we've only gotten to one part of the story, which is events that have happened in the last few hours or maybe the last few days. Those are typical retention times that we would use with the technology like Pulsar. And this is where Iceberg comes in. So as we think about this backfilling problem, we need access to long histories of historical events, like definitely greater than 30 days, usually something like multiple months. Increasing retention of the topic can be expensive, and it's also not a very great solution because you can't query these things as easily with batch engines today, and we also need to delete data, so an immutable log does not lend itself to deleting data very easily. And that's just due to user privacy and compliance mandates. So this is where Iceberg is something that really shines. So Iceberg is a table format, it's not a file format. It solves a lot of the headaches that you have with raw files on cloud storage. And the important thing for us is that it's cost-effective, vendor-agnostic, and that we can read events in a streaming-friendly way due to something called event time alignment, which is built into the Flink Iceberg connector. And so this issue of time keeps coming up, and what we want is these kind of time-ordered reads in the system with minimal code changes, and that's what Iceberg allows us to do. All right, so putting this all together. When you are an engineer and you write this job, you can deploy it at will. It will use the same production data in development as it would actually in production, so you have the same kind of output and behavior that you would see there, even if your kind of development job is well isolated from production, which is great. You start your job maybe months ago or even a year ago at a timestamp in the past, and these raw event data are read from this Iceberg table in this event-ordered way, and that's what allows us to have this kind of smooth watermark behavior that I've been talking about. The backfill has now started kind of making progress. We're getting closer to the present, accumulating state, outputting results, and like I said, things are still stable because even with a gigantic quantity of data, we're able to process it all incrementally. But we're catching up to the present. And then there's another very special feature of Flink, which was also open sourced by a company. So like I said, the open source element of this is a huge benefit. We're not the only one trying to solve this problem. Is how do we switch from a batch source like Iceberg to a streaming source like Pulsar? And there's an open source thing called the hybrid source, which allows you to combine multiple Flink sources together and make them a truly kind of seamless source. So it abstracts it away from any of your engineers from ever having to think or care about this, which is really the nice goal. So all that happens under the hood is it just picks a timestamp and you switch from one source to the other, and everything is totally seamless. And so we just abstract it all away. So what we have here in this system is really cool. This is our kind of refined architecture, which has fewer moving parts. We have access to all the different event types that we want. Our engineers don't have to care about where they come from. They're served with this proper partition-style delivery, so we get those low-lag watermarks. Diving into that Flink job, it houses all of our feature computations, which are filters, aggregations, joins, et cetera. We run this thing once over a long, multi-month period, dump the results to an Iceberg table, and that's our training data. You can train a model on this, and then the machine learning component of it really comes in through something called Onyx, which is an open neural network exchange format. So you can use tools like XGBoost, PyTorch, TensorFlow, make your model in any system that you want, and then convert it into this ONNX format. And what we do is take that binary and load it with the ONNX ML inference library. And this can happen directly in your Flink job. So now you don't need a separate service. And the potential for bugs, like with stitching and trying to mix all these different sources together by hand, which are really hard to debug, they're just naturally at a lower probability of happening. So it can make kind of development faster and just simpler in a way. And this is not a new idea. This is effectively just saying, this is a Kappa architecture instead of a Lambda architecture. But the cool thing is, like, you can build this even with a really small team. So this evolved kind of design is more robust, it's more streamlined, and it has that point-in-time accuracy of all the features in the system that you really need when you're trying to do machine learning for real. And again, on top of the simplicity, our ML engineers can just iterate. They can make changes to this system and backfill it within just like 3 or 4 hours, train a new model, and deploy it, and then see kind of what's going on. So this is an image of our Flink UI just to show you that these jobs really do allow you to get quite complex. It integrates all of the things that I talked about, multiple data sources, multiple aggregations, joins. We switch into process time to do very low latency joins because, again, speed is really, really important to us in certain cases. We can do all sorts of custom logic in these process functions. It's great. And the ML model is just like one little square on there. The whole, part of this talk is building the data for these ML models. Well, deploying it for inference is just one little square on this graph. It's so much simpler than having to spin up a whole separate service. You can't do everything with this, but you can do quite a lot. And so many of our models we can run in this style of system. And then we have syncs to both output stuff to Iceberg, Pulsar, anything that we want at the end. Flink really does give you this kind of amazing capability. And now I think the other great thing to report here is, like, we don't have to think about deployment as much. We built these custom Basel rules that abstract away all of the authentication, the persistent volumes, all these details that our ML engineers don't want to care about. They can just put in any of the kind of regular Flink configs, point it to their job application, and we take care of all the details of containerization, pushing, and even deployment. And again, in that theme of like the power of open source, the deployment is also kind of managed to us. The Flink Kubernetes operator deserves a call out here because this is a custom resource definition. We prepare it and we launch this resource into our cluster. And this operator takes care of the whole life cycle of Flink jobs. So this is deploying it for the first time, taking save points. It includes high availability and a number of other features that are really, really great. So since we've deployed this system, we've had multiple like double-digit metric improvements on internal safety metrics for both the spam area and the account security area. So we really are making Discord a safer platform and protecting our users. And we're just really, really thrilled about that and trying to think about like, what else can we use this awesome system for? So I'll get to the conclusion now. What we've built is a mature, production-ready ecosystem for doing ML in real time, end to end, and it really is enhanced by the maturity and the connections between Flink, Iceberg, and Pulsar all together in this kind of trifecta. I talked about why ML has this certain requirements around backfill and trade-offs around time, and we've kind of solved that real-time state problem and backfill limitations in this system that we built. I mentioned that we achieved this kind of critical metric impact and that we were really excited about this technology. So this is kind of like a journey of a thing that we built, and now it's prototyped, it's in production, and we're like migrating more and more stuff to it. You can use this for other things other than ML. We have ideas to do like faster A/B testing, better experimentation. I mentioned moving into our personalization domain. That's a whole nother area of ML that this thing can possibly improve, like certain problems that they're working on when time and speed and this kind of point-in-time accuracy really matter. Like I said, the message here is this whole system was built at Discord with a very tiny number of engineers, and we basically rely on the amazing open source community that has tried to solve similar problems and donated this stuff. And I think that's something that you should really think about if you're trying to build something like this at your own company. The kind of technology has kind of hit the critical mass where you can build really, really powerful stuff. And I think that is just really, really cool. So think about that if you are starting your journey into streaming. And so with that, yeah, I'll take questions. Thank you. Yeah, so the question is, do we use on-prem or managed Pulsar? So what we originally did when we were prototyping and testing out kind of what we wanted to potentially migrate to off of PubSub, we deployed Pulsar using, I think, there's an open source Helm chart. We didn't use the StreamNative one. I think it's through Bitnami. So we originally did that. But right now we use a managed Pulsar cluster through StreamNative. Anybody else? Yeah, one right here.
Is your historical replay done through Pulsar?
Question is our historical replay done through Pulsar? So partially. So we'll keep some of the events, like hours or like maybe a few days in Pulsar. But the key is, like, for us, we need replay that is over a much larger time scale, like months or even like years. And so all of that comes through Iceberg. And that's what's kind of neat, is that you can get something that's close to a stream that you would get out of Pulsar. Like, the ordering guarantees are worse, but those don't really matter during the backfill phase. So we combine them.
So it's replay. So you're not using like a source connector to connect Iceberg to Pulsar?
So no, not to connect those two together. So we use the Iceberg connector, and then we use the Pulsar connector, and then this neat hybrid source lets you say, okay, I want to use both of these as a kind of abstracted single source, and it will take care of the mechanics of doing the switchover for you at a predetermined timestamp. Anybody else? Yeah.
So why not Kafka?
Yeah, so I tried to hit on this, but we have a ton of queue applications, and Kafka at the current moment in time, I know they have a kit to make this. They don't support queues, and so there's certain applications where partitions are really not good. Like if you have thousands of workers, you don't want to have to always have 1,000 partitions. Like, scaling up and scaling down is kind of a pain there. So most Discord applications are all running on these queue-style event systems, and so we want to be able to support that ideally in a single system, and so we kind of get both. Yeah. All right, well, thank you very much for coming. Oh, we got one more. Okay, we got more.
Do you have experience with Kafka partitions? Do you feel comfortable making comparisons?
I don't really want to make like comparisons to it. So I have experience like managing it and doing things like rebalancing, but probably not enough to make like really deep technical comparisons. I will say that the Kafka connector also does have a very high quality connector, and that's a very popular use case. And so, like, when we were thinking about what we wanted to use, it came down to those two. It's what has been in production, what's been around for a while, has most of the bugs kind of figured out. We're probably not going to hit the limits of these systems, but we want it to be open source, that we could manage it if we had to, but we don't want to. And it needs to have a Flink connector that is active and maintained and that people use, because otherwise you kind of end up with maintaining it yourself, which is not fun. Yeah. All right, great. Thank you so much.
Awesome. Thank you so much, David. That was amazing. So I just want to let everybody know we're going to take a very quick 5-minute stretch break. So if you can meet back here or in the other room, our breakouts are going to start in about 5 minutes. So in this room, we're going to have CJ from StreamNative and Yingjun from Rising Wave, and they're going to talk about streaming data into your lakehouse. And we'll have Abib Kinan from Axon doing platform observability in Pulsar in the next room over. So that's just, if you got this door, turn right into that room. That's going to be the other breakout session. And also for those sessions, for our Q&A, we do have this microphone box. So don't be afraid to look around and have this thrown at you. All right, see you all in a couple minutes. Thanks, everybody.